right, so we'll take our first fundamental theorem here. We'll go back to the problems we did from yesterday. We'll pick up where we left off. For these problems from yesterday, now we need to define some intervals on the original integral. So on this problem here that we started yesterday, let's let our interval be -2 to 1. What that now does to this problem, well, it still tells us we have to take the antiderivative of the original function, which we did over here. But all this plus c stuff, we can now take that out. Plus c has to do with the indefinite intervals. This is now definite. We'll be able to get an exact value answer. Plus c is no longer relevant. Instead, what we do after taking the antiderivative, we throw a little bar over here to basically explain that, all right, I've taken the antiderivative, but I haven't yet acknowledged the interval. So on this little bar, I put a little -2 at the bottom. I put a 1 at the top because, hey, that defines the interval for me. Now, if I go back to what this theorem states, we know that f is the antiderivative. All I have to do is take this top value here, plug in, take this bottom value here, plug in, and subtract the two ideas. So if I go back here, I'm going to take the top value of 1. I'm going to plug into my antiderivative, so I have 1/4 times 1 raised to the 4th. And then I'm going to subtract. Take your -2, plug in. So 1/4, got -2 here, raised to the 4th. See if you've taken the antiderivative. Now it's just a matter of plugging in some numbers and doing some calculations. If we do the calculations, well, let's see. Over here, we're going to have just 1/4. Here we got -2 to the 4th, so that's 16, right? That'd be 16 over 4, which, yeah, I know is 4, but let's keep the common denominator because if we subtract through, then we're going to have -15 over 4. I think that's going to be the value now for our definite integral. In fact, if I go back here to our directions, right, really I should change these directions too.
How'd you get the subtraction?
Here, hold on a second. Let me change this to evaluate, because that's what we're doing now. And on this first one, evaluating the value is -15 over 4. All right, on the second example from yesterday, our interval that we're going to define here, we're going to start at 1, go to 2. And we've got the process here of finding the antiderivative. We've gotten down to this point, right, where we know what the antiderivative is. As I mentioned on the previous problem, though, plus c stuff, no longer necessary. What we need to do instead is show that we're at the point where we've taken the antiderivative, but we still have to consider the interval. So we throw the little bar in there to show that consideration. On that bar, we put in our interval values. And since this is our antiderivative, we're simply going to start with this 2 here, plug in for the x values. So we're going to have 2/5 times 2 raised to the 5/2 plus 2 times 2 raised to the 1/2. All of this is the substitution for just the 2 value. We are taking that and we are subtracting. For the second one, we're just going to plug in 1. If we plug in 1, we've got 2/5 times 1 to the 5/2 plus 2 times 1 to the 1/2. Of course, all those 1s, so we raise those powers, we're just going to get 1, so you could just say 2/5 plus 2, right? there is some calculating to be done on this one. You know, I'm probably going to resort to the calculator, honestly, to do this one to make a little more sense out of my answer. If I resort to the calculator to do this calculation, find that answer, then do this one, find that answer. Subtracting the two, what we should get in the end, I've already done this one. Let me find that for you. In the end, we should get 2.69 as our exact value answer. Okay, on the third example from yesterday, if we define an interval for this one, interval, since we're working with trig stuff, we're actually going to use some radian values here. We're going to start at pi over 4. We're going to range up to pi over 3. Got the antiderivative in place from yesterday. Going to take out the plus c since we now have a definite integral to work with. Over here, we recognize that we still have to apply that interval. So we acknowledge that with a little bar. In applying the first fundamental theorem, start with the top number, plug into the antiderivative function that you found. You replace that x, be negative cosine of pi over 4. We're going to subtract then, or I'm sorry, it'd be pi over 3, wouldn't it? So negative cosine of pi over 3. We're going to subtract then, plugging in now the pi over 4 part, the negative cosine of pi over 4. Obviously double negatives here, we can just make that addition. Nice time to review the unit circle. Got negative cosine of pi over 3. We're looking at the x value. That would be at pi over 3. The x value that would be at pi over 3, I'm sure we all remember, is negative 1/2, right? Might have a better chance of remembering the next one. If you take the cosine of pi over 4, the x value of pi over 4 was root 2 over 2. There we go.
In the unit circle is the x value with cosine.
On the unit circle, the x value is the cosine, and the sine would be the y value. Got common denominators here, so we can put this together. We'd have negative 1 plus root 2 all over 2, and we could leave that as our answer. Could also here, since we're talking about an exact area anyway, calculate it out to the decimal. That would be acceptable. But either way, we got the idea on how to apply the theorem, so there is your answer. All right, so here on number 4, if we introduce a definite interval here, now let's see, interval is going to go from 2 to 4. So if interval is going to go from 2 to 4, as we carry our integral notation through here, well, over here everything was still in terms of x, right? So this is still going to go from 2 to 4. But now here's the trick on these u problems. I mentioned yesterday how when you get down to this point and you've taken the antiderivative, like we now know the whole plus c stuff we don't need anymore. Honestly, we don't need this step either, as long as we make a quick little calculation along the way when we introduce u as a variable. See what we can do back here at this step where we've gone through and we've set up our new and improved problem. Since we know u is going to equal x squared minus 1, well, let's go back to our interval values here. Let's take this top value of 4, which is supposed to be in terms of x. Let's plug 4 in over here. 4 squared, going to be 16 minus 1 gives us 15 back. We could put a 15 up here. And now everything in terms of values is going to be in terms of the same variable u. At the same time, I could take this 2, plug in for what u equals, Got 2 squared 4 minus 1, so 3. Got my value of 3 down here, also in terms of u. So if I take the antiderivative to this step, knowing I still have to acknowledge the interval is going to go from 3 to 15 as long as I'm keeping things in terms of u.
How did it jump from 3 to 15 plugging in?
Yeah, what's nice about this is that you don't have to go back, resubstitute the x stuff in at the end, then do what could potentially be a greater calculation with the numbers that you're given on the interval in the first place. If we just pick up where we're at now, plugging in 15, we'd have negative 1/2 be 15 to the negative first. We're subtracting then the negative 1/2 be 3 to the negative first. If you want to rearrange some negative exponents here and do the calculation, that'd be fine. If you just want to start hammering things out in the calculator, get the decimal value back, that'd be fine. All right, so if we take the calculator route, the value is going to be the 0.13. If you take the cleaner route of finding the fractions and doing all that, the answer is 2/15. All right, if we look at the next one from yesterday, this one also involves some u substitution. If I define an interval to start with, we'd have 0 as where we're going to start this interval in the original problem. We'll go up to the square root of pi over 2. We'll see why we selected a value like that here in just a moment. But in terms of transferring information over to the work that we did from yesterday, I already talked about this on the previous problem. You know, all this plus c stuff, we no longer need that. In fact, this last step here where we replaced u in terms of x, we don't need that either, as long as we make our change on our interval when we go from everything being in terms of x to everything being in terms of u. So if we make this change over at this point, where we were just setting up the new and improved problem in terms of u, and we know that we're starting our interval originally at 0, we now know that u equals x squared, so that 0 was an x. If I plug in for x, obviously I get 0 back, so interval over here has to start at 0. But for the square root of pi over 2, if I know that's in terms of x, and I plug that in here to figure out my u, well, I'm squaring that root in the numerator, I'm just getting pi. Squaring that 2 in the denominator, I'm just getting 4. You get a more user-friendly radian value now that you can plug in. So at this stage here, that's the antiderivative. Got to acknowledge the interval. As long as we have our antiderivative, just plug in. Got negative 3 cosine of pi over 4 minus negative 3 cosine of 0. Got your double negative. Just for old time's sake and for fun, let's use the unit circle again. Got negative 3 times the cosine of pi over 4, so the x value of pi over 4 again is root 2 over 2. So it's negative 3 root 2 over 2 plus 3 times the cosine of 0. The x value at 0 in the unit circle is 1. So it's just going to be adding on a 3 here. I'd say as an answer goes, that's sufficient. If you want to calculate out the decimal, though, that'd be fine too. All right, so last one from yesterday. We did have to introduce u on this one. We need an interval, though, to start with. So the interval on this one to start is going to be from 0 to 1. we clean up some of these unnecessary parts, taking the plus c's out, taking this last step out where we introduce the x back in. Now try to set up a new interval at this point in the problem, right? Because at this point in the problem we've changed our variable. If I go back, I know that x was 0 originally to start the interval. I'm plugging in 0 down here for what u equals. Obviously I'm getting 0 back. If I take this 1, again plug in, it's 1/2 times 1 to the 4th, just going to be 1/2. That's going to be where this new interval ends. This was my antiderivative. Set up my little bar here to acknowledge the interval I still have to plug in. Use the fundamental theorem to plug in. As I plug in the 1/2 for u, I've got e to the 1/2 minus, plug in 0 for u, I've got e to the 0. Or if you do a little maintenance here, you could leave it as e to the 1/2 or write it as the square root of e. But definitely this e to the 0 I could change over to 1. All along understanding that, hey, I could hammer it out in the calculator too, get my decimal values, round off to a couple decimal places, get the exact area answer that way.